already.
Hello everyone. Today we'll be giving our presentation on a maker's guide to FE sensors on a budget. So the problem we're trying to address is that commercial force torque sensors are expensive and it's hard for makers to access them. And our goal is to show you how to build and acquire force torque sensors without sacrificing functionality and accuracy. Today we'll be going over various FE sensors, how they work, what makes them expensive, and maker-friendly alternatives. And if you didn't know, force torque sensors measure force and torque across 3 different axes, and there are various sensing modalities which we'll be talking about throughout this presentation.
So most current 6-degree of freedom force torque sensors are made for industrial applications, and they're made to be very precise and low noise, and to be very repeatable. So they're hundreds, if not thousands of dollars. And they have certified accurate calibrations usually, and that's good and all, but for makers like us, or hobbyists, or startups, we want affordable sensors, which means, first up, we want a low BOM cost. Second, it needs to be accessible, which means it shouldn't require fancy tooling to manufacture. And third, it would be great if there's open source CAD, schematics, or code, so DIYers have a starting point for their own custom versions of these sensors. In addition, even research labs that can afford one of those $10,000 sensors will very much benefit from having cheaper sensors, because that opens them up to novel geometries with like sensor arrays, or being able to have tens of different sensors on different robot joints. So clearly, we need cheap force torque sensors. So as useful robots grow, like their costs go down to like $20,000 for a humanoid, or $1,000 for an arm. To make them useful for manipulation tasks, we need cheaper tactile sensing. And it doesn't really make sense to have a $1,000 arm that has $7,000 fingers. In addition, a lot of form factor flexibility is needed for tightly integrating end effectors with tactile sensing. And most household and hobby manipulation tasks don't really need the millinewton precision that the super precise industrial sensors offer, and something on the order of 10 grams or 100 millinewtons is fine, so there's no point overbuilding.
So we believe that low-cost force torque sensors come in all types of forms and factors, but we believe that these are a pretty good representation of this work. Next slide. So starting off with, next slide, Vision, which is the paper that we sent y'all. Vision, the main way that it works, it's got 4 main components: a static camera to sort of view a medium which will deform due to external interaction, some sort of lighting element or something to help the camera actually view the medium, and then an algorithm to process it. On the processing side, you have 2 main types of algorithms. You have your analytical or classical types, and then your data-driven. Your data-driven is like your CNNs, transformers, whatever. And then your analytical approaches, from what I had seen for force torque sensing, involves either getting displacements from consecutive frames of sort of markers, or using like a perspective and point approach to get a relative transformation and rotation of like a marker that you can use for deformations. So what makes these sensors awesome is that you're able to abstract a lot of these hardware issues into awesome computer vision software and detect cool things like gestures and force normals. And the result of that is that you end up with a lot of like kind of fingery force torque sensors or force sensors, which is great. But what we're looking at is sort of the more pure type of force torque sensor, just 6-axis, you get it. Another issue with these vision approaches is that the data rate's pretty slow. Because cameras can't get past like 100 hertz. So we picked our fiducial sensor. The way that it works is it's able to basically, using background information it has of the QR code, it's able to generate that relative rotation and translation to see like how the QR code changes with changes in forces. And the reason we picked it was because it fits pretty much everything that we could want. It has pretty good performance, it's really affordable, it's open source, and because of that, it is #1 on our tier list. Ta-da! So with that, we'll stop now because we just talked about the paper. Were there any questions on the paper?
I noticed that on one of the figures that they actually had, it was like the fiducials were like tilted, like they put
Like
on
this
like
one?
little tilted.
Yeah.
Do they have to go through like a in-depth like calibration to make sure that that's actually like the zero of the sensor?
So, they're able to have it be somewhat inaccurate because at the end of the day, you're just looking at relative changes in the QR code. So like, assuming the platform kind of moves uniformly-ish, you're able to get, you will need to calibrate it, right? That's where you're gonna get your linearized model from. But that should be accounted, like any funky stuff with like where you put your QR code, assuming you don't put it like somewhere silly, like the very corner or whatever, should be accounted for in the calibration.
I have a question. When you have some type of torque, you also like have a shear force, and sometimes the thing in the middle can deform. When you're twisting.
Like if it's like really tight and
Yeah.
it like kind of crosses
Yeah,
each
it
other.
starts like crossing. So do you think if you have something that is detected that, wouldn't the torque itself would deform the QR code in such a way?
Oh.
You know?
Like touch the QR code?
Not touch the QR code, but when you start doing the twisting motion, the QR code is not gonna stay, how you say, like a square, but it's gonna start maybe shifting like a rombo or something like that. I don't know.
So,
I would imagine that's just outside of the bounds of like the sensor like recommended ranges of forces. Because at the end of the day, every sensor needs to have some sort of limit for how much force you can apply. That might just be one of them.
What would you say was like the main downside of that sensor?
of this sensor, I would say main downside, a big part of it, so, you can't quite get as accurate as a like commercial grade. That's just the unfortunate truth. Also, like if 25 hertz is not fast enough for your application, that was the data rate it had, by the way, it was like 20 hertz. So if that's not, gonna work for your application, then that's,
And also FZ on fiducial sensors is pretty bad because you're kind of just changing the size of the fiducial, not really, and it's less obvious than if you shift it in the other axis.
On the paper, they compared its sensor to like industry grade sensors. Will you be comparing it to other cheap sensors?
yeah, so after we get through these questions, and we should probably limit the next actual couple questions so we can get through it. But yeah, next coming up, we'll talk about the other modalities as well. So yeah, you have a question?
Oh, yeah, I have a question. So, of course, once you build the sensor, you need to somehow get the actual force out of the sensor. So, once I have it built, I need to know that this much force means this much displacement. So, of course, you need the whole calibration process. And if you want it really good, you do need a force torque sensor to calibrate it. So,
Now, what is cool about this is it's a linear model. So as opposed to like a neural net or something like that, you don't actually need as many like points of reference to get like a fully calibrated model. I forget. It was like 6 by 6. So what is that like? That's 6. I don't know what it is off the top of my head. But they actually did talk about, just being able to take like a string and, being able to calibrate it that way. They do use a commercial force torque sensor to do the calibration, but in the paper they do reference being able to not do that as well.
And we're also planning to do that with our project, is to be able to just use string and maybe water bottles as varying weights in 6 degrees.
Anyways, let's get to the next slides, sorry.
So now we'll talk about other cheap force torque sensor options. And one of these is an optical sensor that isn't camera based. Instead, you're looking at the change in intensity of light to tell your forces and torques. And these aren't inherently 6 degrees of freedom, so if you wanted a force torque sensor, you would take multiple and put them together to get that higher dimensionality. These sensors are comparatively lightweight, compact, and they're good for low to medium forces, so you'll see them a lot in like fingertips, small robots, but there's also room for variation in form factors and range. The way they work is you'll have something sending light, something receiving light, and in the middle, something that deforms to block or change the angle of the light or the intensity. If you were to manufacture it, you'd probably have something like a PCB with your electrical components, some kind of elastomer, or something that is moving, and then finally, you'd have an outer case to package the whole thing up. This means that they're usually pretty easy and straightforward to manufacture. And one paper I wanted to highlight shows how accessible it can be. This paper shows a whole family of 3D printable sensors that have a variety of form factors. And what's cool is that the designs are all open source and they give you your own tools for not only firmware and code, but also calibration, CAD, and everything you need to basically design and make your own force torque sensors. And not only is it very accessible in this way, it's very well documented, but when you make them, they're pretty low cost, under $30. It only takes a few hours of printing, and as you can see, you can even make sensors that extend beyond the small range and can go up to like 20 newtons and all kinds of different form factors. And so in general, optical sensors are faster than camera-based, they're compact and lightweight. They're pretty simple and cheap to make, but you could have issues with like light interference and other noise, so there could be accuracy issues, especially in a DIY setting where you're having to get that precise alignment yourself. And then, because of not only the documentation, but also the general performance, we've put this type of sensor in the A category.
Why is it less?
So I would say that like the camera-based sensors can they are slower, but you can also get pretty decent performance out of them. Generally speaking, we're also doing like general versus like specific sensors as well. And so like camera-based could include like more than just fiducial that could have like higher resolution. And also the optical ones, I'd say are probably a bit harder to manufacture for a maker because like with the fiducial one, you can just like buy a camera and then put it in your sensor. You don't have to deal with like the PCB and all of the design stuff. So I'd say that makes it have the potential to be a bit more maker friendly.
Where's the lens? I didn't realize there was a lens.
The top one or the second one?
For this one.
This one is an optical sensor, and so it's a photo interrupter sensor. So the way it changes is that you have, you see the little fins? They go in there and they block the light, and so that's a deformation that causes your change in intensity. And then that is being incorporated into that cylinder.
I thought you said there was a lens that's hard to manufacture, but this looks like there's no lens?
Oh, I don't remember saying lens,
Okay.
sorry. Did I?
I think it did say that, but it, maybe, yeah,
Okay.
I think it's,
Okay, yeah, moving on to our next type of force torque sensor. So we have strain gauge force torque sensors, and these are kind of what you see on the market, the ones that are very expensive. So how these work, they use unique rigid geometry with embedded strain gauges, usually in a Whetstone bridge configuration, which and those bridges are sounds like before. Once deformed by force or torque, the foil pattern on the strain gauges are compressed and stretched, and those forces are then converted into readable electrical signals. However, these are very highly complex to manufacture, and an example is the ACI Nano 25, which is a commercial sensor. So, kind of like what Maddie said, strain gauges aren't necessarily 6 degrees of freedom, so you can actually use uniaxial strain gauges for different types of applications. So, for instance, we have a torque sensor for robotic joints. These are a lot lower cost than your commercial force torque sensors because they're used for specific applications and they're easier to manufacture. So for this one, this was a paper-based one, it was less than $125, but it is limited in application. And in general, 6-degree of freedom high performance sensors are very high cost due to manufacturing costs. Also, they're just a lot more complex. And as an example, we have the KW75EC, and those are all usually at very high price points, around $6,000, $7,000. An example of a low-cost 6-degree freedom sensor is the sewer platform one. It is low cost, but it is a little bit spottier and has less of higher accuracy, but it is 3D printed and is more maker-friendly compared to commercial 6-degree freedom sensors. So what are the pros and cons for strain gauge force torque sensors? They have excellent linearity and precision, fast frequency responses, highly accurate and stable, easy integration into mounts, so can be used in a lot of different applications. However, like I said before, they're super expensive. This requires high quality circuits, very high manufacturing time, and just requires a lot of complexity. They're also sensitive to temperature drift and can sometimes be difficult to calibrate if you're making your own. So that kind of goes into the one that we chose. So this is a user-friendly, economical 6-axis force torque sensor. The reason we chose this one is because it is on the cheaper side, relatively speaking. It is less than $1,000, but obviously, if you're a maker, that's still very expensive, but a lot less expensive than those other $7,000 price points. The reason that it's less expensive is because it uses a unique geometry design, which lowers the manufacturing cost, and uses different manufacturing techniques, which can be done in like a university lab. And it's still pretty big, but it's still robust, has a very high performance, close to commercial sensors, but generally hard to manufacture. Because of that, that sensor would be placed into C tier because of the reasons just stated. It's still pretty inaccessible, still very costly, so kind of a middle range sensor, and then commercial sensors are just inaccessible to makers because of how expensive they are.
Next, I'll be talking about capacitive force torque sensing. As most of you know, a capacitor is composed of 2 lead electrodes, and then and a dielectric. And in terms of force torque sensors, this dielectric is usually compressible, such that when you compress the sensor, the distance between the 2 electrodes changes, as well as the cross-sectional area, which affects the capacity side. Just to highlight 3 main sensing modalities. First is CoinFT. It consists of 2 rigid PCBs with cone traces on them, and then the dielectric is the silicone pillars. Second is this fabric sensory sleeve. It's a strain sensor that utilizes screen-printed electrodes onto the fabric. And lastly is this dot view sensor, which is an array of electrodes that tells you how much pressure is applied to the sensor. This sensor also uses a camera, which looks at the array and can tell you where on the sensor pressure is being applied, as well as the direction of shear. And as you can see, capacitive sensors take on many different types of form factors and are made of different types of materials. Moving on to pros and cons. They're very low cost, compact, and lightweight, and as you saw from the previous slide, they're highly customizable, whether that's your electrodes or your dielectric or the material or geometry that your capacitive sensor takes on. And adjusting these properties can help makers adjust their sensitivity of the sensor to their liking. But when making capacitive force torque sensors, it's important that you consider the hysteresis of your dielectric. For example, if you compress your dielectric, will it decompress or spring back to the same thickness it was earlier, and how fast will it do that? It's also susceptible to environmental noise if shielding is not applied correctly, whether that's EMI or parasitic capacitance, and it requires complex calibration due to its nonlinear response. From all these sensors, our favorite sensor is CoinFT, not at all biased. So we chose this because, one, it's really easy to manufacture. It relies on methods that, it relies on methods that makers are already aware of or know how to do, like PCB and silicone molding. While it is pillars, you can also have like just a solid sheet of silicone and try to mimic that. It's relatively good in performance-wise. It's cost-efficient, under $10. And as I said, it's customizable and it's open source. And for that reason, we put it on the S tier. And we put, on the other side of capacitive force torque sensors, we put the dot view sensor on the B tier, because the paper claims that it's low cost, but doesn't really specify like a number in the paper, and it's actually pretty hard to like space out your array, and then you have to like buy a camera, expensive. Moving on to barometric sensors. Barometric sensors are made up of low-cost transducers that are sealed to a hollow cavity. And then when force is applied, the air pressure within the cavity increases, and then your chip reads that, detects that, and converts it to a digital value. I looked at two different types of barometric sensors. First is the 6 degree of freedom sensor. It uses a rigid 3D printed top and bottom plate with a rubber layer in between each rubber. There are four units of rubber, each with 2 barometric sensors in them that detect that, and that allows you to detect all 6 axes of force and torque. On the other side, we also have the multimodal barometric and IMU sensor. It can detect changes in pressure as well as orientation within space. So pros and cons, these devices offer extremely low cost, mostly because they're mass produced and off the shelf. They're also robust and durable. And then these chips come with a lot of functionality already built into them, like the transducer, the signal amplification, and the ADC. And on the other side of cons, they're pretty sensitive to temperature and changes, well, because it's air pressure, and changes in altitude. And then they're very fabrication dependent, your performance, because they must be perfectly sealed so you don't have any leaks. And then since pressure is only one-dimensional, to measure more degrees of freedom, you're going to need more sensors to do that. An overall best sensor is the 6-axis MEMS barometric force torque sensor. It's 6 degrees of freedom, which allows makers a lot of it opens up a multitude of options. It's very accessible with 3D printing, rubber molding, and the chip that already has a lot of functions built into it. It's pretty cost efficient, it's customizable. You can adjust your rigidity and compression based on your geometry and rubber, and it performs pretty well. And for this reason, we put it in the A tier, mostly because it's kind of, well, this specific one is pretty bulky, but it is 6 degrees of freedom, so that offers a lot of options for makers.
Okay, so Hall effect force torque sensors are essentially magnetometers on a PCB surrounded by a body that holds a couple of magnets, and the distance of those magnets to the magnetometers changes, which changes the strength of the magnetic field, which can be interpreted as forces and torques. So there's a couple of cool Hall effect sensors to note. The first one in the top left is a magnet powder blended with silicone rubber. It's very, very promising. It can be used in soft robotics, and it increases the range of existing Hall effect force torque sensors by a lot. But it's only 1 degree of freedom right now, so it's not very useful for our comparison. MagTac is a 6-axis fingertip, which uses 3 magnets and a plastic spring kind of thing to be able to sense forces on the finger moving around. eFlesh is very cool because it's fully 3D printed. It measures force and the position of where the forces are applied. So usually Hall effect force torque sensors are extremely easy to assemble relative to a lot of the other ones. They don't have like goopy silicone stuff. The form factor is very flexible because at the end of the day, you just need to move the magnets closer and further from the magnetometer. So you can do that in a bunch of different geometries. And the update rate is very fast because magnetic sensing is a very mature technology. But the big con with magnetic sensing is that interference can be really bad, and you have to really try to shield it because motors, which exist in robots everywhere, emit stray magnetic fields, and that can interfere with the sensing of the magnetometers in the force torque sensor. So my favorite sensor out of these is MagTac because it's 6 degrees of freedom. It's a little expensive at $80, but it uses relatively accessible parts. It's just 3D printing and laser cutting plastic. And the best part is it is 6 degrees of freedom and updates at several hundred hertz. It takes around 3 hours to assemble, and the sensitivity can be very easily adjusted by changing the pattern on the laser cut spring element. And communicating with it is trivial because it's just I/C magnetometers and relatively simple math. that can be done on a microcontroller. So, because MagTech is kind of complicated to assemble, even though it's very useful, it has a lot of small screws, a lot of very tiny 3D printed parts that need to be printed with a small nozzle. I'm putting it in C tier, and then eFlash, insanely easy to assemble. You literally just start a print on any regular FDM printer, slip some magnets in, slide in a PCB, and that's it. So it's going into A tier, and what I call the squish force torque sensor with the magnet powder embedded in silicone rubber is going into B tier because it's very promising for soft robotics, but it's only 1 degree of freedom.
So in conclusion, we've looked at 6 categories of types of force torque sensors that could all be possible alternatives to an expensive commercial one, and each one has its pros and cons. If you want something effective that can be easy to make, you've got your camera-based sensors, but they have a slower data rate. If you want something faster that's also lightweight and compact, you've got your optical sensors, but you have to be able to tolerate some deformation, they're not as stiff, and there can also be like light, noise, and accuracy issues. Strain gauge sensors are classic. They can be very reliable and high performance, but they're bulky and you have to pay for that performance. After that, capacitive sensors are robust, they're cheap and compact, but they're sensitive. Not only sensitive in a good way, but also to noise and interference. Barometric sensors are also robust and cheap, but you have to be able to manufacture them well since you can't have any leaks and you'll have to make multiple of them to get a force torque sensor. And then finally, you've got magnetic sensors, which are flexible, customizable, good for soft robotics, but you have to be really careful about that EMI. And if you want to compare cost versus performance, we tried graphing this out. So we have 2 graphs because something we found is that it's just really hard to compare these different sensors. Not only are they giving us different metrics like R squared, mean squared error, or maybe percentage, but they're also collecting different data in different ways, whether it be torque or force. So ultimately, it's just not a clear apples-to-apples comparison at all. And we gave some recommendations, but if you want to try making some of these decisions yourself, we have this decision tree. That being said, this is just our best guess off of what we've seen in generalizations, but there are always exceptions to the rules, there are always counterexamples, and ultimately, this could go in very, very many different ways, just depending on your needs and your application. And with that, that's our presentation, and thank you for your time. Are there any questions?
Hey, I have a question. Can you go back to the blue sensor, the fingertip. If you keep going back, I think.
Oh, the eFlash?
Yeah, that one. No.
The blue one?
Yeah.
That one. So you were talking about like torque, but I thought when we read this paper, it was more about position and.
Yes, this only measures force and position of the force, but it's very clever use of hollow side sensing, so I included it. And we can use it for force, which is very useful in a lot of applications.
But why is it so high in the tier list if it doesn't measure what you're tiering listed for? Like, you're trying to measure torque, right?
Horses and birds.
Horses and torque?
Yeah, that's
okay.
That's a good point. I mostly included it because it's cool for the application that it's intended for, but that's a very good point that it should probably have been lower.
Okay. Like as a maker's friendly sensor, it is exceptional.
I think also, yeah, there's like 2 kind of areas you can look at the Arculus one from like a 6-degree freedom force torque sensor, like highly accurate, that type of sensor, but also like the actual like maker friendly, and then these types of sensors are very maker friendly but don't necessarily meet our needs for force torque sensors. And I think that just kind of goes into how it's difficult to compare these, but they can be used in good applications if you're a novel robotic system.
Yeah, or if it like it's readapted to be a force torque sensor eventually. Just
Can we see the tier list actually? Yeah.
Where is fork?
14 is not force torque.
almost true.
Yeah.
But we go to the same thing. That one is also not.
This one is, yeah.
I mean, I think if you were going to make a Forte force torque sensor, it would look like that barometric
Yeah.
one. So I'm like,
Doug?
Yeah, for one of the strain gauge sensors, I think it was like, you had some complex manufacturing techniques. What were they?
Which one are you talking about?
I think it was the one that you highlighted as the favorite one.
Oh, so can you go back to the slide? So, I forget exactly what they said in the paper, but in general,
Yeah.
so if you're having like a normal like force torque sensor that you're using for like just industrial use, those have like very high complex like manufacturing techniques. But this one specifically, I forget exactly what they said in the paper, but the techniques that they use for their manufacturing process and also the design they actually made was easily manufacturable like at high scale, which would make the price less. So that's why it was cost less. But compared to other like commercial force torque sensors, those have different geometries and they use different like manufacturing techniques that make them more expensive. So like if you go, can you go to the backup slides? So for instance,
I don't like pick out for that.
it's so like it's the one. Wait, yeah, go back. So for this one, this is an example of just like a torque sensor, but they use like they use different manufacturers. So specifically they looked at different manufacturing techniques, CNC, drilling without precision, and then drilling with precision, and those had different price points. So like that's an example. Like if you use different manufacturing techniques, it like alters the price points. But at the same time, it could lead to different like accuracies within your sensors, and can cause like deformations very easily if you use different manufacturing techniques. So there's kind of trade-offs with both of those, if that makes sense.
For your sensor topics, you have like 6 of them. But what if you choose different amount of sensors for each topic? Like vision only has 1, but another one has like 3.
Yeah, so I think, so I guess that was just kind of like how we divvied it up. With vision, I think I just ended up going with like a broader, I tried being like a little broader in my scope. That was just like a me personal thing. It wasn't explicitly referenced there, but I had leveraged some more like heavier review papers. Like if you go to my slide, the very first one, up. Yeah, like this paper wasn't on like a particular vision-based tactile sensor. It was kind of like a review. And so I think that like the reason that like some of us had different amounts of sensors in others, I think was just like a personal preference.
And
We each took on different sensor types.
I had a hard time finding barometer force torque sensors. So just based on like what's out there.
the lit review. See the last author? He's coming to talk on Monday. Please come if you.
That's
Yeah.
Mr. Guy?
Yeah, Nathan LaFora is gonna come talk. So you should please come to the talk on Monday and Wednesday. Yes, thank you.
If he shows us, because I'll be like, hey, we cited
No, straight up. Yeah, that's like right. Like why? Are you, that's why we invite them here, because it's like, you know, yeah. Anything else? Or?
Like,